Hi everyone, my name is Milana and I was working on the project 2126, benchmarking scientific software for computational chemistry and HPC systems. My part of the project focused on benchmarking software used to simulate biomolecules. Why do we simulate molecules and why do we need to benchmark the software we use? Molecular dynamics or MD simulations are a powerful tool for studying dynamics of biomolecular systems. They act as a computational microscope that allows us to overcome limitations of the conventional experimental methods, limitations such as studying processes happening at the atomic level and on sub-microsecond timescales. When performing a simulation, the computer needs to calculate interactions between the atoms for every step of the simulation, and the more atoms there are, or the more simulation steps we want to perform, the more computational power is needed. Therefore, most of today's MD simulations are done on HPC systems. So by benchmarking representative systems, we can help the HPC users to choose the optimal setup for their simulations. In order to simulate a biomolecular system, we need a model and a force field. A model describes a molecule as a collection of points which are assigned coordinates in Cartesian space, mass, and charge. Models can be atomistic, where one point is equivalent to one atom, or they can be coarse-grained, where one point represents a group of atoms. How these points interact is described by a force field, which consists of a set of equations called potential energy functions and parameters that are used in them. The computer solves these equations for every atom and calculates their coordinates in the next step of the simulation. Depending on the model that we are using, we're going to use different force fields, and some of force fields offer much better performance compared to the others. So, how do we parallelize a simulation? When we simulate a system, what we actually simulate is a box with the molecule of interest, water molecules, and ions inside of it. We could simulate one such box on a single core. However, it will take a really long time to calculate all the interactions in such system. What we can do is decompose the box into domains and map them to MPI ranks so that a single MPI rank handles all calculations within one domain. Naturally, we would want the parallelization to scale linearly. However, that is in practice possible only for a small number of cores and also depends heavily on the algorithm that we use and the size of our system. The software I was benchmarking was GROMACS, which is widely used for MD simulations and has very well implemented options for parallelization. I benchmarked 3 systems, 1 atomistic and 2 coarse-grained. The simulations were run on both the CPU and the GPU nodes, and I also compared the performance of GROMACS compiled with different tool chains. If we look at the performance and scaling of the coarse-grained algorithm on the CPU nodes, we can see that both versions of GROMACS compiled with FOSS toolchain offer better performance as measured by how many nanoseconds per day we could simulate, and also better scalability as measured by R². There are some differences in the performance between the systems, which can be explained by the difference in the number of atoms and how they are distributed in the simulation box. But if we look at the atomistic model, we can see that for a system of this size, both compiling options show almost linear scaling, with the FOSS toolchain again performing better. What we can also see is the massive difference in the performance between coarse-grained and the atomistic algorithm. So coarse-grained algorithm can achieve up to 50 to 60 times more nanoseconds per day than an all-atom algorithm. However, this increase in performance comes with a significant drawback: loss of detail. GROMACS also offers offloading some of the calculations onto a GPU if there is one present. Again, the all-atom algorithm shows almost perfect linear scaling, but now for both algorithms, GROMACS performs better if it was compiled with the Intel toolchain. The drop in the performance on 7 nodes for the coarse-grained algorithm is a result of suboptimal domain decomposition in these 2 systems. Another interesting thing is that the performance between the GPU and the CPU nodes is actually quite comparable, but considering that the GPU nodes usually have fewer cores than the CPU nodes and that the usage of HPC systems is paid in core hours, it is cheaper to use the GPU nodes if they are available. That is all from me. Thank you for your attention, and special thanks to my mentor Anna, co-mentor Carlos, my project mate Sahin, Summer of HPC organizers, and Prince.